Okay, so let's go back. Last class we solved this example problem using modified Goodman method, and we figured out how to find the number of cycles to failure in case we have a non-zero mean stress value. Okay, so what did we do? In short, for this particular state of sigma A and sigma M, we figured out what is the equivalent completely reversed loading using certain formulas. For example, using the Goodman equation, we try to find what is the equivalent reversible load, and then using these values, A and B values, we substitute and we find what is the number of cycles to failure. Okay, so this is for ductile materials. Now we have seen four different equations: Goodman, Gerber, Soderberg, and ASME elliptic. So these were the four different equations. Again, if you recall from your book. So these are the four different equations. Additionally, you have SWT and Moreau. These equations are also available. All these are for ductile materials in general. Okay, so let's go back to the slide and see what is the corresponding equation we use for brittle materials. In the case of brittle materials, we do not use any of the four theories what we have seen before. Rather, we use Smith-Dolan locus. So this is the theory we are going to follow. I wouldn't call it a theory again. It's an empirical equation which we follow for brittle materials. Okay, so what is the difference? There is some difference in the equation. So first, let us see the graphical representation of the failure envelope for Smith-Dolan locus, and then we will come back. So in this example problem, you are given how a Smith-Dolan locus looks like. Now, if you compare, let's say, to the other theories for ductile materials, you can see all these curves looking from bottom, they are convex. Yes, example, your Gerber curve or ASME elliptic, while looking from bottom, looking from top, it is convex. Okay, from bottom it is concave. Or we go back to the Smith-Dolan locus, it is not convex from top, but concave when looking from top. So the shape changes. In the first quadrant, when the mean stress is positive, this is the failure envelope. This is the shape of the failure envelope. But when we go to the second quadrant, something also is different in the case of brittle materials. In ductile materials, what did we have? Let's take a look at it. So maybe a little bit clearer picture. Okay. So here in the ductile materials, when the mean stress is negative, we just consider only the SE value as the failure envelope. What is SE? Is the endurance limit. And if we are below endurance limit, infinite life with negative mean stress, above it, we have failure. Okay, not just finite life, we are here. So after finite life, failure is that. Okay. So now, if you take a look at the brittle materials, on the other hand, instead of having a flat failure envelope, what we have here is, with increasing mean stress, the endurance, I shouldn't call it endurance limit, rather the failure envelope, you can see the amplitude of stress which the material can carry, brittle material can carry under compressive mean stress values is pretty high. It increases. Okay, so this is the failure envelope. So let's see the equation. There are two quadrants again. First quadrant, second quadrant. First quadrant is for positive mean stress. Second quadrant is for negative mean stress. So what are the equations? The first quadrant here, fatigue failure criteria, is given by this equation. So this is the equation we need to follow SA over SC is equal to this particular equation. Now with the factor of safety, how does it look like? We do not have the factor of safety included. With the factor of safety, this is the equation to be written. Okay. If you draw a radial load line in the first quadrant, what is the intersection point? Okay, so in the first quadrant, the intersection point is given here. SA is equal to this value. What about SM? To get SM value, we can take this SA value and substitute in this 651 or 650, and then we should be able to get the SM value from the equation. In the same way, if it is in the second quadrant, the intersection point between the radial load line and the second quadrant failure envelope is again given this. Why are we given this? Because we want to figure out what is the factor of safety graphically. We can use this. Again, what is the radial load line? Go back to the graph here in the first quadrant. This is the radial load line. If this was your calculated values of sigma A and sigma M for your component, and we can see the intersection point. This intersection point is A value is given by the equation. In the same way, if it is negative, if it is in the negative side, SA value is again given by the other equation, intersection point between the radial load line and the failure envelope. Okay, so let's see this example problem. We have a plate, a grade 30 gray cast iron is subject to a load F applied to a 1 by 3 by 8 inches. Okay, this is 1 inch, and the thickness perpendicular to the board. Remember, this is the cross section. Okay, you are shown cross section on top of it. If you look at the cross section, let's say from this point of view, you will see this rectangle. So cross section dimensions are given with 1/4 inch diameter hole drilled here in the center. The surfaces, so mostly cast iron are brittle materials, by the way. The surfaces are machined in the neighborhood of the hole. What is the factor of safety? Guarding against failure under the following conditions. So since it is a brittle material, we will have to use KF. Okay, that means we need to figure out KT. These are constant capital KF and KT. These are stress concentration factors. Okay, let's read what is the factor of safety. Okay, if the load is equal to this many pounds, tensile steady. So it is a static case. This is a static case. The load is 1000 pound force repeatedly applied, which means varies from 0 to 1000 pounds. So this is cyclic. And the third case, the load fluctuates between -1000 to 300 without column action. So we need not consider any effects like buckling here. That's what he means. So fluctuates between these loads. Use Smith-Dolan fatigue locus in the B and C cases. So let's see here. I'm not going to find what is the fatigue stress concentration factor. We will briefly go through here on how to do that. Table A24 gives you the material property. So if you go to your book, you can figure it out. SUT value, we need, since it is a brittle material, you will have SUT and SUC value. They are different. And you are, okay, so let's see here. A24, we might just take a look at it. Let's go to appendix. '23, 24, and this is aluminum, grade 30, I think. Let's rotate this. Okay. Okay, so these are all gray cast iron. So this is the correct table. We have to take a look at it. Grade 30, we are given SUT, SUC. You can see shear, elasticity, and what else? Endurance SE, endurance limit SE directly given. Okay, so this is the, let's see, what is the value here? 14 kpsi. In the problem, we are given here. So how did they, okay, here 14 kpsi, yes. Okay, and what else? So these are the data. Here, endurance limit, you are given for polished machine specimen. It is not explicitly given. What kind of SE values are given here? Let's see here. Okay, it doesn't state specifically what kind of SE values are given here. Usually, okay, what have they mentioned here? So here we can see Ka and Kb values are already included. Ka is the surface modification factor. In the case of brittle materials, these are already included. We have to assume these are included here, and Kb is the size modification factor that is also included. The Marin factor Kc for axial loading is taken to be 0.9, and then they evaluate SE value, and final SE value they are going to use is this. So all these material properties are required. SUT, SUC, and SE value are required. Okay. From table A15, we can get the stress concentration factors, KT. So this is the standard method. You will get it as usually. And the Q value, not sensitivity factor, Q, is again obtained from one of the graphs. We have gone through this already, so I'm not going to repeat it. So after that, we calculate what is the capital KF value, because at this particular region, we want what is the stress concentration factor to calculate the stresses. How do we calculate the stress? Force over area, Kf times force over area, and we can evaluate. Before we go there, let's see here. This is part A. It's a steady state force. What does steady state mean? From fatigue point of view, F max and F min are equal and equal to the force value, whatever value you have, which is given to be 1000. Okay, 1000. So what does this mean? That means also my sigma max and sigma min are going to be equal, 1000 over A, whatever is the area of cross section. Max and min are equal, implies what? My sigma A will be, since it is sigma max minus sigma min, amplitude will be 0. Sigma mean stress is going to be same sigma max or sigma min value. And that is what we have calculated here. The mean stress is there, but the amplitude is 0. So whether to know if failure will take place or not, the simple for the simple case, we can take the sigma mean stress value. It is positive. Okay, so since it is positive, we can take the SUT value instead of the compressive stress value. We can take the SUT value and directly calculate what is the factor of safety to figure out whether failure will take place or not. And we get 6.75, no failure. So first case is extremely simple. The second case is 1,000-pound force repeatedly applied. What is repeatedly applied? It means between 0 and 1,000. Okay, so again in this case, F max is equal to 1,000, sorry, and F minimum value is equal to 0. That means I can calculate what is the F amplitude. F amplitude will be F max minus F min over 2, 1,000 minus 0 over 2. This is what I get. In the case of F mean value, it will be F max plus F min over 2. That is also equal to 1,000 over 2. So both are equal to 500. Then it is easy to calculate what is the amplitude and mean stress with the stress concentration factor directly. They should be equal, and this is the value we get, kpsi. Okay, so clearly we can see sigma A and sigma, mainly sigma M is positive. We have to use Smith-Dolan locus. Which quadrant we are? We are in this first quadrant. Okay, and what is the value of A and M? 2.3 kpsi. Go to the diagram. This will be your 2.3 kpsi. Okay, right here sigma M is 2.3, sigma A is 2.3. We can draw a radial load line, join these 2 points, extend it. It will intersect at some point. We need to find the coordinates of these points. What's the equation to be used? Go back. This is the SA value. Okay, so what are the values of SUT? In the positive quadrant, we have to use SUT. Okay, and substitute the values, SUT, SE values. But what is R? R in our case is simply on the radial load line. R will be equal to sigma A over sigma M. Both values are equal, therefore it is equal to 1. So if you find SA value, SM value will be also equal, because R can be also written as SA over SM. Okay, so this is the SA value, SM. Okay, so use this formula, substitute. R we can substitute, SUT, SE values are known. And if you do that, I'm not going to do the calculation, it is already calculated here, 7.63 kpsi. Okay, now again, if you want to figure out whether you are inside the limit or outside the limit, then again we calculate what is the factor of safety, N. If you want to do it according to the graphical method, we need to get the values of the length OA and OB. Okay, so N will be OB over OA. But what is OB? Since this length and this height are equal, we can simply use Pythagoras theorem and write it as 7.63 root 2 divided by OA is going to depend upon this value here. Sigma A and sigma M values are 2.3, equal values. So using Pythagoras theorem, if you calculate this hypotenuse, 2.3 root 2. You can cancel off the root 2's and then calculate the factor of safety, 7.63 over 2.3, and that is what we have here, 3.32. Very simple case. Third case fluctuates between -1,000 to 300. So let's go to part C. Okay. F max is 300. F minimum, sorry, minus 1000, right? Where is it? Minus 1000. Negative 1000 value. Okay. So we have the max and minimum value. What is FA? FA will be F max minus F min. So minus of minus becomes plus over 2. And this is the value we have. Similarly, F mean stress value will be F max plus F min. We get minus 350. We have FA and FM values. Again, it is a tensile load. We use the stress concentration effect 1.29 times FA value over the area of cross section gives you the amplitude of stress. We can calculate the mean stress and it is negative. So we are in the second quadrant here. So let's plot the radial load line with these coordinates 2.98 minus 1.61. So minus 1.61, 2.98. So this is the point we have to consider. We draw a radial line and it intersects the failure envelope here. Let's call this point D, and we use the same method to figure out whether failure occurs or not. We find the factor of safety OD over OC. Use the Pythagoras theorem. Okay, so before that we need to find the intersection point D. In the second coordinate we are given what is the intersection point. This is the formula to be used, especially when the mean stress is less than 0. So just substitute all these values we have, substitute and figure it out. So let's see what is the calculation they have done. This is the intersection point. You can see SE and SUT values being used. We can substitute here, and let's see here. We have the SM value. So in the formula, you can see there is the SM value. In this formula, we didn't have the SM value. We could directly calculate SA value. Since we have SM value here, there is a problem here. How do we calculate? Okay, to do that, first we need to calculate what is R. R is calculated as sigma A over sigma M, and this is the value we get. From here, from the R value, we can also write it is equal to SA over SM, where SA and SM are the intersection points. This intersection point. From here, we can replace SM. SM is equal to SA over R. Put it inside here. We have SA on the left hand side, SA on the right hand side. So we need to solve for it. Say SA is equal to SE plus open SE over SUT minus 1 times SM. SM I'm going to replace with SA over R. We already have the R value. So bring the terms commonly out here to the left hand side. Take this term. I don't know why this is not appearing. Okay. So take this term, second term, and take it to the left hand side. If I do that, I'm going to get 1 get plus 1 over R. The right hand side I will have SE times 1 plus let's say 1 over, if I take SE commonly out, we have, no, actually I think I wrote it wrongly, since we have SA over R here multiplied. Let's rewrite this. So we will have 1 here. We have to take the entire term here. We will have 1 minus to the left hand side. So let's open up another bracket here. SE over SUT minus 1, the whole multiplied by 1 over R is equal to SE. Okay, so now we can rewrite the equation. We will have SE over 1 minus this term, entire term. One over R. Okay, so that is the equation given here, and we substitute and we calculate. We get the intersection point 18.5, and here they have taken as SA over sigma A gives you the factor of safety. May not be very clear. If you use the Pythagoras theorem, you will see you will get the same value as well. So we can calculate SM here. So this is 18.5 kpsi in the problem according to the calculation, and the R value is negative 1.86. The SM will be 1.86. So that will give you the SM value. So that's right, 18.5 will be your SA value over right, yes, negative 9.94. 4 kpsi. We can calculate the factor of safety in this particular case as OB over OC. I think OD over OC, sorry. According to the diagram, OD over OC. So use the Pythagoras theorem. Instead of writing 9.94, we can write 9.95 as given in the problem. (18.5) square plus 9.95 square divided by, use Pythagoras theorem for OC as well. What do we have here? Sigma A and sigma M values 2.98 and 1.61. 0.61 square. So if you do that, you will see that you get the same factor of safety value. Okay. Now, why have they written SA and sigma A here? Because R, you will see that R will factor out and you will be left with SA and SM values. We can also derive that separately. Okay, so if you want to see the length OD, it will be written in terms of SA square with SM value. SM can be written as SA over R. Okay, SA over SM, yes, square, and we can see, we can take the SA value commonly out. In the square root, we will have 1 plus 1 over R square. In the same way, the length OC can be evaluated as sigma A square plus sigma A over R whole square. Again, we can see sigma A times 1 plus 1 over R square. So OD over OC, if you divide these two quantities, if we were to divide them, we can clearly see we have a common factor which can be taken out and can be written as SA over sigma A. Okay, so that's why by taking this ratio also you can calculate what is the factor of safety N, and we get 6.2, which means we are well within the failure envelope and no failure takes place. Okay, so in the case of brittle materials, you will not be asked to calculate what is the number of cycles to failure, because we do not have the empirical equation. For the case of cast iron, a formula similar to the steel material. Okay, so what is the formula I am referring to? Specifically, if we go back, this formula. Okay, we do not have this formula available for the case of gray cast iron, and therefore we will not solve for the number of cycles to failure type problems for brittle materials. Again, you are given here some points. The endurance limit, whatever is listed in the table, it includes Ka and Kb values for gray cast iron. Okay, so whatever endurance limit you are given, that will be Ka times Kb times Se prime. That value is given, and Kc value for axial and torsional loading is taken to be 0.9. If it is bending, Kc will be equal to 1 for bending. Okay, so these are the conditions. Okay, so we are done with brittle materials. We will also see equations in the case where we apply torsional load, how to solve the problems. But before we go there, we can take a 10-minute break. Let's meet again at 9:10 and we will continue the class. Okay, so let me see the timings. Ramadan timings again. I think we have 8 to 8:50, 9 to 9:50. So from 9:10 to 9:50 is the class. So let's meet again at 9:10. Okay.
Okay, Doctor.
Yeah. 9:10. Yeah. Okay, shall we continue? Are you guys there?
Yes, Doctor.
Okay, we'll continue now. Okay, so we'll start with the torsional problems. Okay, in torsion, how do we use the equations? So first we need to realize under pure torsion with no axial or bending moment loads, under just pure torsion, you will have only shear stresses. Okay, so let's go back to those tables which we have seen before. Let's see, maybe in this version of the book, this doesn't have the tables. So let's go back here and search for the tables. Goodman. Okay. Okay, so instead of using the tables, let's first go to the equations we see here. Under torsion, we do not have the normal stress, normal amplitude or normal mean stresses. So what should be the equation I should use under pure torsion problems? So let's go here. Before this, I'm going to open it up again. Okay, now it seems working. Pure torsion case. Okay, so under torsion, we have only shear stresses and no normal stresses. So what is the equation I should use here? So if I were to write the modified Goodman equation, or the Goodman equation here, in this case, sigma A over SE is the original equation. I have to replace with a tau A over SE. Okay, so what is the difference? I will let you know. And here plus sigma M over SUT. So the same equation becomes tau M over SSU. For this is for ductile materials again. Should be equal to 1 over n with the factor of safety. Okay, so here instead of writing SE, we have written here SSE value. Okay, so this is the shear endurance limit. In the same way, instead of writing SUT, I have written here SSU value. So we need some method to figure out SSE and SSU values for our particular case. How do we get it? So let's go back here. Testing has found that steady state component has no effect on the endurance limit of torsional loading if the material is ductile, polished, notch free and cylindrical. So this is a very important point. The endurance limit does not change and it has no effect with respect to shear stresses. It has no effect the mean stress value. So what is this saying? It doesn't matter what my tau m is, whether it is positive or negative, the endurance limit remains the same. What is the difference between the previous and the present one? In the previous one, we can see as sigma m varies, my failure envelope varies. That means we can say the endurance limit or the fatigue limit changes depending upon the sigma m values, but in the case of shear stresses, we need not worry about it. We just take the SSE value. Okay. However, for less than perfect surfaces, so this is true for ductile material, well polished, notch-free cylindrical surfaces. So, however, for less than perfect surfaces, the modified Goodman line is more reasonable. So we can use the modified Goodman equation for other cases. Okay, so less than perfect surfaces. For pure torsion cases, use Kc equal to 0.59. So we have seen the Kc value for bending is equal to 1. For the tensile cases, we can use a different value. For torsion, we use Kc, the Merin factor Kc as 0.59. We also need to figure out or estimate the value of SSU value appearing in the modified Goodman equation, and we get SSU value by this empirical equation. So this is important to know that how you calculate the ultimate strength in shear using the formula 0.67 SUT. So this is the formula we can use. SUT value can be obtained from the tables, and SSU can be estimated by using this relationship, especially for most of the materials, steels and cast irons and any ferrous material. Okay. Okay, so let's see here. If they have given any estimate for SSE value. Apparently in the slide, we don't have anything mentioning the SSE values. So in that case, we'll have to search the book for a corresponding equation. Okay. Yeah, the combination of the loads for brittle materials, apparently not in the new version of the book. Maybe we need to check it in the old version. This is the combination. Okay, so we have more relationships here. Okay, from the previous chapter, we also have seen using distortion energy theory. This is another one we will require. So I'm going to just note it down in the equation here. Suppose if we use the yield line, we also need the formula SSY. So how do I find 0.577 SY? So from the yield strength value, we can find SSY value as well. So these equations in general will be provided to you. Okay. And let's see, endurance strength. For the endurance strength in torsion. Again, we are not given for the endurance strength in torsion SSE value. So mostly SSE value will be given in your problems. Okay. So these are the two equations that are of importance here to estimate the values of SSU and SSY. Okay, so this is pure torsion case. What about the case where we have combination of loads? How do we deal with it? Maybe we have a bending moment load and torsional load acting together, just like a shaft. If you take any shaft, you will have combination of these loads. How do we deal with that? Just as we dealt with in the static case, we will use the same von Mises stress idea from distortion energy theory. We will use the von Mises stress idea and evaluate von Mises amplitude of stress and von Mises mean stress. So how do we calculate them? So this is the formula to be used. And what is the load factor we have to use? The Merin factor. Okay. So you know there are 6 different Merin factors: Ka, B, Kb, Kc, small kc, etc. Specifically, the load factor should be used always Kc equal to 1 for the combined load. Since we have combined load, that means we may have torsional load, bending load, everything together. Okay, always use in the case of combined load Kc equal to 1. Why? The effects of Kc in torsion for example, or in bending, they are already included in this formula given here. So therefore, we use Kc equal to 1. We can see for the axial load, the Kc value equal to 0.85 is already included here. And for the torsional load is included by the factor 3 that appears over here and here. Notice that between the mean stress and the amplitude of stress, there is some difference. For the amplitude of stress, we use the Kc value 0.85 corresponding to the axial load, but in the mean stress, we do not use that. Okay, so this is a standard formula. You will apply this formula with Kc value equal to 1 and then calculate SE value and do the problems. Okay, so this is for the von Mises stress. How do I use these von Mises stress? Where do I use them? You will use it in the same way as we have solved problem with the pure bending moment load or axial load. Okay, so which means I will use it in the Goodman equation, Gerber asemi-elliptic and Soderberg equations. Wherever the terms sigma A or some other terms appears, there I will replace it by corresponding values. See here. So let's take the Goodman equation. Sigma A over SE plus sigma M over SUT equal to 1 over N. So this is the Goodman equation. All I am going to do is, in the case of combined loading, I'm going to replace sigma A over with von Mises stress amplitude and von Mises mean stress values in the equation. So this is Goodman. If you have Gerber equation, in a similar way, you will replace with the von Mises stresses. Okay. Von Mises stresses, these two stresses. And you will do the same kind of calculations for the life. Okay, so if you want to calculate the life, again, you will find the equivalent von Mises reversible stress, and you will use the usual formula to calculate your number of cycles to failure. The procedure will be exactly the same. Okay, so this is for fatigue, but when you use a Goodman equation, you will have to combine it with the yield failure criteria. Yield failure criteria gives you that you will have to calculate what is the yield factor of safety, and that will be calculated as y over von Mises max stress. Von Mises max stress is evaluated by using this particular formula. Okay, you can also calculate von Mises max stress approximately by using the formula here given here. If you add these two quantities, you will get it here, but it is better to use this particular formula to evaluate your von Mises maximum stress accurately. So let's see an example problem how to apply this. And you have combination of loads. So rotating shaft is made out of 42 by 4 mm ASI 1018 cold drawn steel tubing and has a 6 mm diameter hole drilled transversely through it. Estimate the factor of safety guarding against fatigue and the static failures using Gerber and Langer failure criteria. The shaft is subjected to, you have two different cases, completely reversed torque 120 Newton meter in phase with completely reversed bending moment load. So this is important. Why it is given in phase? Otherwise, the situation will be more complicated. So if you take the torque is applied like this, and let's take the blue color to be torque, and on top of it, I'm going to draw the bending moment, and bending moment is also in phase. So same frequency. This is bending moment. So this is in phase. So when torque reaches maximum, bending moment reaches maximum. If they are out of phase, the situation will become a little bit complicated. We are not going to solve those kind of problems here. Okay, so let's go back to our OneNote and try to solve the problem. Okay, so what we are given here, let's try to draw this pipe here. Let's say this is the pipe we have, and remember that it is a hollow pipe. A pipe is always hollow, so that means we have an inner surface which is invisible. Okay, and it is hollow right in the center. What we are given, the dimensions are 42 by 4 mm. So let's see if I'm sure. Yeah, 42 minus 8. Okay. The diameter, outside diameter, is 42, and the thickness of the pipe is 4 mm. So let's call this capital D. Okay. And we are going to use the, as given in the book, same symbols to represent. Small d to represent the inner diameter will be equal to 42 minus 8, because 4 mm here, 4 mm here, and we'll have 34 millimeters. Let us see, inner diameter. Okay. Now, in addition to this, in the problem you are given, it has a transverse hole drilled into it, which is 6 mm diameter. Okay. So let's say before this, let's say we drill a hole. That means we drill a hole like this. Transversely, there is a circular hole of 6 mm diameter here. Which means if I take a look from the top, I'm going to see a hole over there. Okay, so the presence of the hole will give the pipe some stress concentration effects, and we'll have to take that into account. Okay. Okay, so what we are asked, a factor of safety. We have to calculate the factor of safety, both yield factor of safety and the fatigue factor of safety for this problem. It is a combination of torsional load and bending moment load, both being completely reversed load in the first part. Before we go there, we also need to extract all the properties of the material, ASI 1018. Steel tubing. From the tables you should be able to get these values, so let's get these values. It is a ductile material, so as usual we will need SY, SUT, etc. 370 megapascals in SI units, and here we have 440 megapascals, and which means SE prime value can be estimated. SE prime is 0.5 times 440 gives 220. Then we will have to also extract, get the values of Ka, Kb, etc. Okay, we are using the 42 mm diameter value to calculate the Kb here, and we get the values, and then we estimate SE to be 165. I'm going to directly use that. I'm not going to calculate each thing, each material property. So for the Gerber criteria, we need SUT value, SE value, and SY value for the Langer line or yield line. We have all the material properties. The next step is fatigue stress concentration factor, which we are supposed to evaluate. Now, unfortunately, now this is going to be a little bit complicated here. Okay, why is it so? Need to go to the tables and figure it out. Okay, so first thing is we need to go to table A16. Okay, so what is A16? You can see for bending of a round bar or a tube. So this is the table which has to be used, a hollow tube with a transverse round hole, exactly the same kind of problem we are solving. So 1013. Where did we go? Table 820, right? Sorry, 16. I think we went forward a little bit. 1016, 14. I think 13. Yes, this is the table we want. Okay, so there are two different tables we have to deal with. One is a torsion application, and then bending moment application. So these are the two tables which we have to consider. It has a transverse hole with a particular radius A. Okay, and we need to extract two different values. One value is A, because we are directly given how to calculate the Z net value. Since we have a bending moment load, we need to calculate that and then evaluate what is sigma naught with specifically the transverse hole of a particular size. So this will involve some interpolation to be evaluated. So first let's see here, what is the A over D value? 0.143. I'm going to do one example here, and you will calculate for torsion by yourself. So first let's take a look at the table here, and we can see A over D ratio. Let's see, I'm going to write A over D ratio. We will need, because we have to do interpolation, we will definitely need three different values. And what is the A over D ratio for our problem? You take it 6 over 42. 6 is the diameter, outer diameter 42, capital D 0.143. Again, you can see A over capital D. Okay, 0.143. I'm going to write that right in the center. So this is the value we are required, for which we need to calculate them. Okay. let's go here. On the horizontal, we have small d over capital D. Go back to the problem. The ratio 34 over 42 gives 0.810. So let's see here. I'm going to write here capital D over here, make it into 3 columns here, and then we have the value 0.810 right in the center. Okay, so why did I write like this? We will see that. Let's go to the table and compare here. 0.143, A over D is 0.143. Do we have it here? We definitely do not have it here. So what are the values? 0.143 is between 0.125 and 0.15. So I'm going to write 0.125 and 0.15. It's between these two values. And on the other hand, capital D over small d, what is the value? 0.810. And we can see it is between 0.9 and 0.6. Let me get rid of this line. It's not required here. Okay. Okay. A over D. Okay. Okay, so now we have to copy in the values of A. Corresponding to 0.125 and 0.9 is 0.82. Is the value of A, capital A. So let's see here. I'm going to combine two different things, capital A and K. Those two values we need to interpolate. Unfortunately, we have too many things to interpolate. QT. Okay, so let's see. 0.1, 0.82 and 2.41. Okay, so this is the value. And here 0.79 and 2.39. And we do not have values in the center. Let's see for 0.6, 0.82 and 2.32. 2.32. And here we have 0.79 and 2.29. 0.79 to 2.29. So we need to find both these A and KT values for the given problem. So here and here. What we can see here is for the A value horizontally, the value is equal, does not change between 0.9 and 0.6. So definitely it does not change for the case of 0.810 value. So straight away I can write here 0.82 over here. And in this region also I can write 0.79 for A. So it simplifies our situation, at least for A. But we need to calculate for 0.143, and therefore I need to find the value here, the interpolated value. We can use the linear interpolation formula to evaluate what is A. for the value 1.143. Okay, so what is the linear interpolation formula I should use? To find A, I write the equation 0.82, this is the value, corresponding to 0.125. Okay, then if I use the interpolation formula, the value changes between these two values. So I write it as 0.79, the final value, minus the initial value 0.82, corresponding to these two values, 0.15 minus 0.125. So that gives the slope multiplied by the change in value here is 0.143 minus 0.125. Okay, so that gives us the A value which we can interpolate. Let's see here, 0.82. Bracket open. Each bracket we need to fill in. 0.79 minus 0.82. In the denominator we have 0.15 minus 0.125. And then we have 0.143 minus 0.125. Gives us 0.7984. So we have at least one value, 0.7984. A value. Okay, so we have calculated the interpolated A value. Let's check in our slides. If we have, yes, 0.798, correct value. Now let's go to the other one. We see we have a problem here. We have to do interpolation in two directions. First, we have to do the interpolation in this direction for KT. Get the KT value over here, and then just 1 second. Okay, so we have to get the KT value over here and here, and after that we have to interpolate in the vertical direction because it is varying 2.41 2.32. So first we interpolate in the horizontal direction, get the values here and here. Okay, so let's see this value over here corresponding to 0.125. If we use the same interpolation formula, let's see here, we have to use 2.41. Use a blue color. (2.41) plus we take the difference in values 2.32 minus 2.41 for the difference in values of the small d over capital D ratio, 0.9 minus 0.6, and multiplied by, let's see here, we are going from 0.9 to 0.810. So okay, so what is the final? 1 second. It is decreasing. The final minus the initial value 2.41 is negative. I think I have written wrong way here. In the denominator, this should be 0.6 minus 0.9, sorry. Because that's the final value minus initial value. Because we are taking 2.32 minus 2.41. So 0.6 minus 0.9. And here you will have 0.810 minus 0.9. Okay, so we need to calculate this value and then note it down here. 0.41 numerator we have 2.32 minus 41, 2.41, denominator 0.6 minus 0.9, then multiply by 0.810 minus 0.9, get 2.383. So I can write 2.383. Okay. Again, we need to find for this case, what is the equation? We write 2.39 plus 2.29 minus 2.39 divided by 0.6 minus 0.9 multiplied by 0.810 minus 0.9. Okay, between those values. So again, we have here 2.29 minus 39. And here we have 2.39. We get 2.36. Okay, so now we need to do the vertical interpolation to get the value over here. Again, we have to write the equation in terms of values given here and here. So we have 2.383 we do vertical interpolation. 2.36 minus 383 all divided by the value is 0.15 minus 0.125 and here we will have 0.143 minus 0.125. Okay, so this interpolation will give us the value which we require. So let's see here. We have 0.15 minus 125 in the denominator, one for right, 2.36 minus 383. 2.36, 2.383, then we have 383, 2.383 again. 383. Okay, so this gives us 2.36644. So that's the value. Okay, so these are the values of EA and KT we should use in the problem. So let's go and check in the problem. KT value 2.366 they have used. Okay. Now finally, we also need to get the fatigue stress concentration factor after getting KT. To calculate the fatigue stress concentration factor, you need to calculate what is the Q, notch sensitivity factor, which is usually obtained from a graph approximately, and we get the value as 0.78, substitute and calculate what is the fatigue stress concentration factor. We need fatigue stress concentration factor also for the case of shear. Okay. How do we get it? Again, we need to get KTS value. Okay, so to get KTS value, again we go to the table, a different table. This is for bending moment. We got A and KT values. There is another table for your torsion case, and you will have to get KTS value, and again the A value to be used in calculation of J net. Okay, since we have torsion and bending moment, okay, we have torsion and bending moment, so we need to evaluate Z net and J net of after getting all these values according to the formula. Okay, so let's assume we calculated all these values and we have all the quantities, the A here and A here, they are different values. You can see 0.89, 798. After using interpolation, you will get all these values. Substitute, we get Z net and A net. Okay. Now, after that, after you do all this, okay, then you are ready to calculate these stresses. So what are these stresses? Stress is calculated by the formula Kf m over Z net. So this is the formula to be used, and if it is amplitude, you can put the amplitude, and the moment values are given in the problem. For part A, we can see 120. So in this particular case, since it is completely reverse loading, max value is equal to MA value should be equal to 120. Okay, and the mean is equal to 0. That means sigma m is equal to 0. So we can directly calculate. Kf is known, Z net is known. We can calculate in the same way for torsion. Tau A should be equal to Kfs Ta over let's see, we calculate from the value given here. This is the J net value. We can go back. You can put J net value times C. Okay, the C will be 42 over 2. Diameter, external diameter is 42. 42 over 2 will be the C value. The tau m value will be identically equal to 0. Why? Again, it is completely reverse loading. Tau max equal to tau A. Go to the problem and sorry, this is the torque and this is the bending moment. So in which case here it will be 150. 150 here and 1. Yes, I know that. 120, and then the T mean value is equal to 0. Okay, so using all these values, we will be able to evaluate. Next class, we will continue and see the values here and how to use these values to calculate the fatigue factor of safety. Okay, so let's meet again on Thursday. We can meet at the same time, 8:20 on Thursday. So see you guys.
Thank you, Doctor.
Yeah.